So let's just draw that root address strategy now. So we're going to get a base table with how many entries?
4.
Why 4?
4 addresses, sorry.
Why would you say 4?
I was looking at the addresses, sir. We have 4.
No,
Is it
the size of the hash table would be
7.
matched to the number of addresses that would be thrown out.
Okay.
So you have 0, 1, 2, 3, 4, 5, 6. Right? And then from the first position, the first data matched to address 3, so you have a pointer from here. And then this will then point down to the record that would have the data. You have Janet, Brown, and home. And then address 1 and data here. So you point plus space, and then this space there will then point down to the data.
Sir, so why is it for 3 you have the line across?
Here?
Yeah.
Well, it's going to be here also. I'm using it to specify the end of a linked list. Normally, the end of a linked list, I put a special constant inside here to reset null. So here you have Alvin. I will add it also. Of course, if you had something else that had hash to address 3 for argument's sake, then all you do is you come down to address 3, go to the end of the list that was there, and then tag it on. The rest of these that don't point to anything would have null pointers inside them. Now in open address hashing, we'll make sure that our table is big enough to actually hold the data. Of course, we still would have a limited number of addresses, and that number of addresses would have to agree with our hash function. So when we're putting in the first item, Janet Brown home will go to address 3. So you put your then we have Alvin Chipmunk 3 in address 1. Then we have Dogfoot Jail. Then we have Alan Airplane. Now suppose we're going to add Art Jackson, who lived in the museum.
Okay.
If we had Art Jackson, alright.
15 divided by this 1. So you go to address 1.
So this matches it to address 1. So in the close address hashing strategy, where do we put that?
You tag it on to 1.
We then make another node that would extend down here. In the open address hashing strategy, where would it go? If we're using linear probing step size 1,
If you're doing
we'd end up with the data in position 2. Now we can say that the performance that we get out of the hash table will depend heavily on how packed it is. If we have closed address hashing, a search through the hash table will involve first going to where the data started, going to the base address, to the base array, and then it could involve searching a linked list. The average size of the linked list would be dependent on the ratio of the number of items in the hash table to the size of the hash table. And if we have n items in the list, so n is a common term used for the size of the data. And if we have m different positions, then the ratio n upon m actually tells us actually gives a ratio of how packed it is. So the size, the performance of the hash table is also normally written as 1 plus alpha, where alpha is equal to n upon m. The 1 stands for the constant time operation of determining the address. You do a calculation, it always takes the same amount of time. And then alpha will depend on this ratio. If you have more items in the hash table than you have addresses, then of course alpha will be greater than 1, so that will be the dominant term. If on average you have less items in the hash table over a series of operations than you have addresses, then if alpha is less than 1, then you may be getting close to constant time operation. So for small controlled amounts of data, a hash table can give you very good performance, close constant time. Alright, so that's hashing.